In the blackness of lunar night, just before the sun climbs above the curved horizon, something unexpected appears. A soft, luminous crescent, streamers of light, a glow that should not exist on a world with almost no air. Astronauts saw it, cameras recorded it, scientists named it the Lunar Horizon Glow. For more than half a century, it has remained one of the Moon's most enduring optical mysteries. This is the story of the Moon's exosphere, that vanishingly thin envelope of gas and dust that surrounds our nearest celestial neighbor. It is a story that begins with the first surveyor landers and the Apollo crews. It moves through careful quantitative reanalysis by scientists including David Glennar and his colleagues, and arrives at the threshold of Artemis and the long-term human bases we intend to build. It is a story about light scattered by particles, about electrostatic fountains and micrometeoroid impacts, and about the engineering and medical challenges that dust will pose every time humans live and work on the Moon. In the mid-1960s, the Surveyor spacecraft settled onto the lunar surface. After local sunset, their television cameras pointed toward the horizon and recorded a faint, persistent glow. The light was forward-scattered sunlight. The scatterers were dust grains, roughly 5 to 10 micrometers in diameter, lifted a few meters above the surface near the terminator. Later, astronauts orbiting the Moon saw something higher and more dramatic. Crews watching orbital sunrise reported a bright horizon glow and vertical streamers. The Moon has no true atmosphere. What it possesses is an exosphere, a collisionless region in which individual atoms, molecules, and dust grains follow ballistic trajectories under gravity and electromagnetic forces, rarely interacting with one another. The gaseous component is dominated by helium, neon, and argon. Much of the helium and neon arrives with the solar wind. Argon-40 is largely radiogenic, released from the lunar interior. These gases show strong diurnal variations. Argon, for example, freezes out on the night side and is released again at sunrise. The dust component is more controversial and more consequential for human activity. Two primary mechanisms have been proposed for putting dust into the exosphere. The first is micrometeoroid impact. Interplanetary particles continuously bombard the surface, excavating and accelerating fine ejecta. Some of that ejecta reaches orbital altitudes and forms a permanent asymmetric dust cloud. The second mechanism is electrostatic lofting. On the day side, solar ultraviolet radiation ejects photoelectrons, leaving the surface positively charged. On the night side, solar wind electrons charge the surface negatively. Near the terminator, the electric fields can become strong. Submicron grains can be accelerated upward, sometimes described as a dust fountain. In 2006, Timothy J. Stubbs and colleagues formalized a dynamic fountain model. Once a grain leaves the surface, the electrostatic force can give it enough velocity that it coasts to altitudes of tens or even 100 kilometers before falling back. This offered an elegant explanation for the high-altitude glow reported by Apollo astronauts. The qualitative picture left important quantitative questions unanswered. How much dust was actually present? At what altitudes? Was the Apollo excess brightness truly caused by lunar dust, or could residual zodiacal light and coronal structure account for it? David A. Glennar, working with Timothy J. Stubbs, James E. McCoy, and Richard R. Vondrak, tackled these questions directly. In a 2011 paper, the team reanalyzed the Apollo 15 orbital sunset photographic sequence. They incorporated precise sightline geometries into a Mie scattering simulation code and inverted the intensities to retrieve dust concentration as a function of altitude. For monodispersed grains, they recovered a concentration near the terminator of roughly 0.01 particles per cubic centimeter at 10 kilometers. 3 years later, Glennar led a search using the navigational star tracker cameras on the Clementine mission. After careful subtraction of a reference zodiacal light model, no clear lunar horizon glow remained. The non-detections allowed firm upper limits, orders of magnitude below the Apollo inferred values. Similar tight limits emerged from far ultraviolet spectroscopy by the LAMP instrument on the Lunar Reconnaissance Orbiter. Paul Feldman, David Glennar, and colleagues reported upper limits of roughly 10 grains per square centimeter. Because LAMP operates at wavelengths where zodiacal light is negligible, these constraints are particularly clean. These results demonstrated that a dense, persistent cloud capable of producing the bright glow reported by Apollo is not a constant feature of the lunar environment. The Apollo observations may have captured rare events, or the excess may have been partly contaminated by imperfectly subtracted zodiacal and coronal light. The permanent dust population is far more tenuous. In 2013 and 2014, the LADEE orbiter circled the Moon at low altitude, carrying the Lunar Dust Experiment, or LDEX, an impact ionization detector designed by Mihaly Hirani and his colleagues. This mission was designed to resolve the dust debate once and for all. LDEX recorded tens of thousands of dust impacts, mapping a permanent, asymmetric cloud of ejecta particles sustained by continuous micrometeoroid bombardment. Densities are typically just a few particles per cubic meter, orders of magnitude too low to produce the bright glow reported during Apollo. LADEE closed one chapter and opened another. The Moon does possess a dust exosphere, but it is primarily an impact-generated ejecta cloud. High-altitude, optically bright horizon glow appears to be rare or absent under the conditions sampled by modern instruments. While the high-altitude optical mystery has been constrained, the practical dust problem has only grown more urgent. For humans, lunar dust isn't just a scientific curiosity, it is a significant operational hazard. Lunar regolith is the product of billions of years of bombardment in a vacuum. Particles are angular, glassy, and sharp-edged. A significant fraction is respirable, and many grains contain nanophase iron, which increases their chemical reactivity. Apollo experience provided a vivid preview. Spacesuit boots showed significant abrasion, visors were scratched, and zippers and seals accumulated dust that threatened their integrity. Inside the lunar module, the dust floated in low gravity and irritated eyes and respiratory tracts. Harrison Schmitt, the only geologist to walk on the Moon, developed lunar hay fever after breathing in the fine dust. The symptoms lasted for days. The crews described the smell as burnt gunpowder, a reminder of the Moon's chemical vitality. For vehicles and infrastructure, the threats multiply. Dust can jam mechanisms, degrade solar array efficiency, and coat radiators, causing critical equipment to overheat. It is the Moon's most ubiquitous and least cooperative material. Landing and ascent introduce an entirely different scale of problem. Rocket exhaust expands into a high-velocity plume that excavates and accelerates regolith. These particles can reach hundreds of meters per second, sandblasting any nearby hardware. As of mid-2026, humanity has taken the first crude step back toward the Moon. Artemis II completed a successful lunar flyby in April. The next major milestones are the landing missions, driven by SpaceX's Starship, HLS, and Blue Origin's systems. A Starship-class lander produces a far more energetic plume than the Apollo lunar module. Modeling shows that without prepared surfaces, the exhaust will excavate large volumes of regolith, creating a local dust cloud that settles slowly and threatens nearby assets. Spacesuits for Artemis, the XEMU, have been designed with dust resistance as a primary requirement. Even so, every EVA will still introduce dust into the system. Habitats must use filters, cleaning protocols, and suit ports to keep cabin air clean and crews healthy. NASA and its partners have organized dust mitigation strategies under three broad headings: avoid, remove, and tolerate. The cleanest solution is to keep dust away from critical systems in the first place. Electrodynamic dust shields are among the most promising technologies. Parallel electrodes create a traveling electric field wave that levitates and transports charged dust particles off solar arrays and visors with very low power consumption. The ultimate goal of Artemis is a sustained human presence. At that scale, the dust problem becomes infrastructural. Habitats must remain sealed for years, and rovers must operate through abrasive environments without rapid wear. Understanding the natural dust exosphere remains relevant. The scientific legacy of the Horizon Glow investigations is practical as well as intellectual, giving engineers the boundary conditions needed to design systems that can survive and function. The luminous horizon glow that surprised Apollo astronauts has been replaced by numbers. Those numbers tell us that dust is ubiquitous, mobile, and hazardous. Understanding that thin envelope and learning to live with its dust will determine how successfully we return. The silent sky above the lunar surface is not empty. It contains the memory of ancient impacts and the signature of solar wind gases. A journey 60 years in the making, and we are just beginning to stay.